It's like AI is this magic show that everyone's watching, but nobody knows how the tricks work.
Yeah.
We see the rabbit pulled from the hat, but what's really going on?
Right.
The answer is hidden in the math, and that's exactly what we're diving into today.
Right.
The mathematical foundations of AI,
Absolutely.
specifically neural networks.
Yeah.
And we've got this dense research paper breaking it all down.
Yes.
Luckily, our expert is here to help us make sense of it all.
Well, I'm happy to try to demystify some of the denser parts.
So where do we even begin? AI is such a huge field.
Well, a good starting point is supervised learning.
Okay.
It's a core concept
Yeah.
and something that we can all relate to, I think.
Yeah.
Imagine you're teaching a dog a new trick.
Okay.
Show them what to do. You give them a treat when they get it right.
Yeah.
Maybe a little correction when they make a mistake.
So we're basically training the AI like a pet.
Pretty much.
Give it examples and guide it toward the right answers.
Exactly. In supervised learning, we give the AI tons of labeled examples, like pictures tagged cat or dog.
Mm-hmm.
And it learns to predict those labels for new data it hasn't seen before.
Okay, so I get learning from examples.
Yeah.
But how does the AI actually do that? Like, what's the actual math behind it?
So that's where empirical risk minimization comes in.
Okay.
Imagine the AI is like a student taking a test.
Mm-hmm.
It wants to get as many questions right as possible to minimize the errors.
So it's trying to ace the test, but instead of memorizing facts, it's learning patterns from the data.
Right. And to do this, the AI adjusts its internal parameters.
Okay.
These are like knobs and dials that control its behavior.
It's like fine-tuning itself based on the feedback it's getting from the labeled data?
Exactly.
How does it know which way to turn the dials?
That is a great question, and that's where gradient descent comes in.
Okay.
Imagine you're trying to find the lowest point in a valley, but it's super foggy. You can't see anything.
Mm-hmm.
So you might take a little step in a random direction and see if you're going uphill or downhill.
So you're just kind of feeling your way down?
Exactly. Gradient descent is like that it figures out which way to adjust those parameters to decrease the errors.
To move downhill towards the solution.
Yes,
But with so many parameters to adjust, it seems like that would take forever.
you're right. And that's where automatic differentiation comes in.
Okay.
It's a really clever mathematical trick that speeds up the whole process.
So it's a shortcut for the AI?
Yes, a shortcut to find the best settings
Yeah.
without having to manually try every single combination.
Got it.
Now let's move on to the real stars of the show,
Okay.
neural networks.
Okay.
Specifically something called multi-layer perceptrons, or MLPs.
MLPs, they sound complicated.
They can be?
Are those the ones with all the layers, like an intricate network?
Yes, exactly. Think of them as a chain of workers in a factory.
Mm-hmm.
Next layer, processing information and then passing it on to the next one.
Okay, so why are they so powerful? What makes them special?
Well, there's something called the universality theorem.
Okay.
And it says that even a simple two-layer MLP can theoretically approximate any continuous function, no matter how complex.
Wait, so you're saying even with just 2 layers, it can learn to do almost anything?
Yeah, theoretically, yes.
Like, could it learn to play chess or compose music at a professional level?
In theory, yes.
Wow.
That's the incredible potential of the universality theorem.
Okay, but if 2 layers are so powerful, why do we need these massive networks with hundreds of layers that we see today?
That's a great question.
Yeah.
In practice, to get a good approximation, those 2 layers might need a huge number of neurons, like an astronomical number.
Okay.
It's like saying you could build a spaceship with those tiny Lego bricks,
Yeah.
but it would take forever and be super fragile.
So it's a trade-off. More layers with fewer neurons in each makes more sense.
Yeah, it's like using bigger Lego pieces to build that spaceship.
Mm-hmm.
It just makes the whole thing much more efficient and practical.
Okay, so how do we know how many neurons are enough for a task?
That's where Barron's theorem helps us out.
Okay.
It gives us a way to estimate how much better the approximation will be as we add more neurons.
So it's like a guide for how many Lego pieces we'll need.
Exactly. Now, when dealing with tons of neurons, it can be helpful to think about things a bit differently.
Okay.
We use something called the mean field representation.
Okay.
So instead of focusing on each individual neuron, we imagine the whole network as this continuous cloud of neurons.
Okay, that sounds like a way to simplify things.
It is.
So how do we analyze this cloud mathematically?
That's where we bring in something called Wasserstein gradient flow.
Okay.
It's a mathematical tool that describes how the entire network, viewed as a cloud, evolves during the training process.
So we're not just looking at individual neurons adjusting themselves, but the whole network learning as one entity. This is blowing my mind.
It is pretty amazing, and we're just scratching the surface here.
But what about those really deep networks with hundreds of layers? How do they avoid becoming a mathematical mess?
Ah, that's where we enter the realm of very deep networks. And to understand them, we need to talk about ResNet.
ResNet, I've heard that name before.
It's kind of a rock star in the world of deep learning.
So what makes ResNet so special?
ResNet introduced this brilliant idea called residual connections.
Okay.
Imagine those shortcuts in that factory we were talking about earlier.
Okay, yeah.
These shortcuts allow information to skip over some layers, which makes the network much easier to train.
So it's streamlining the flow of information.
Exactly. And what's really fascinating is that ResNets can actually be seen as a way to approximate a differential equation.
Really?
Yeah, remember we talked about the mean field representation where the network is the continuous system? Well, ResNets take that to the next level.
Okay.
Each layer is like a tiny step in a continuous evolution like frames in a movie.
Wow, that's a cool way to picture it.
It is.
So we've gone from simple building blocks to thinking about networks as dynamic, evolving systems.
That's the beauty of math. And now are you ready to jump into the world of generative AI?
Absolutely, let's do it.
Okay.
That's where things get really interesting.
They do.
Generative AI. It's like AI has gone from student to artist.
It really has.
We've talked about those realistic images and text that AI can create.
Yeah.
So, what are the mathematical tools behind this creative power?
One technique that's been making waves is diffusion models.
Diffusion models.
Yeah, imagine you drop some ink into a glass of water.
Okay.
At first it's concentrated in one spot, but over time it spreads out, it diffuses.
So diffusion models are about spreading things out.
It's actually the reverse.
Okay.
We start with a noisy image like static on a TV screen.
Yeah.
And then using a neural network, we gradually remove that noise step by step,
Okay.
guiding the image towards a specific target distribution.
So it's like we're training the AI to clean up a messy picture.
You got it.
But how does that lead to creating something new?
Once the AI has mastered this denoising process, we can start with pure noise and let it do its thing.
Oh.
It'll iteratively remove the noise, guided by the patterns it learned from real images.
So it's like the AI is learning the essence of what makes a cat look like a cat, not just memorizing specific photos.
Exactly. It's learning the underlying structure.
This whole process sounds really computationally intensive, though.
It can be, and early diffusion models were definitely demanding,
Yeah.
but recent advances have made them much faster and more efficient.
Okay, good to know.
Yeah. The math behind how we sample from these models has gotten much more sophisticated.
It seems like every day there's a new breakthrough in AI.
It does, doesn't it?
Speaking of breakthroughs, we touched on those large language models, LLMs, before.
Yes,
Can you break down how those work in practice?
absolutely. Remember we talked about tokens, those small chunks of text the AI works with?
Yeah.
Each token is embedded into a vector space,
Okay.
basically turning it into a set of numbers representing its meaning and context.
So each word gets its own numerical fingerprint,
That's a great way to put it.
like a unique code that captures its essence.
Exactly. And these vectors are then fed into a transformer network.
Right, transformers with that attention mechanism that lets words analyze each other.
You got it. The attention mechanism allows each word to look at all the other words in the sentence and figure out which ones are most relevant to its meaning.
It's like each word is trying to understand its role in the sentence by having a conversation with the other words.
That's a really good analogy.
That's so cool.
It is, and this process happens across multiple layers of the network,
Okay.
allowing the AI to build a deep understanding of the sentence's meaning and structure.
So the AI isn't just seeing words in isolation, it's building this whole web of relationships between them.
Exactly. And once it's built this web, it can use it for all sorts of tasks,
Like what?
like translating languages or writing different kinds of creative content.
That raises an interesting question, though. How does the AI know what to write or translate? Where does the creativity come from?
That's one of the big mysteries in the field.
Yeah.
We don't have all the answers yet. But one key factor is the massive amount of data these models are trained on. They absorb the patterns and nuances of human language from this vast library of text.
So it's like they're learning to be creative by studying the works of countless human authors and poets.
In a way, yes,
Yeah.
but it's important to remember these models are statistical machines.
Okay.
They're fantastic at recognizing patterns and recreating them.
Yeah.
But whether that's true creativity is still up for debate.
It's like the difference between a talented impersonator and the original artist.
Yeah,
The impersonator can capture the style, but maybe not the soul.
exactly. It highlights the importance of not overestimating the capabilities of these models.
Right.
They're powerful tools, but still just tools ultimately guided by human intentions.
It's humbling to realize how much we still don't know about how AI works,
Right.
even as it's becoming more and more powerful.
Absolutely.
This has been an incredibly enlightening dive into generative AI.
It has.
But before we wrap up, what's on the horizon for this field? What are the next big things?
One really exciting area is the development of multimodal models.
Multimodal models?
Yeah, AI systems that can seamlessly integrate different types of data,
Like what?
like text, images, audio.
Yeah.
Imagine an AI that can not only understand a written story, but also generate illustrations or even a soundtrack to go with it.
That sounds like something out of a science fiction movie.
It does, doesn't it?
It would revolutionize how we create and experience stories.
Exactly, and that's just one example.
Wow.
Researchers are also working on making these models more efficient, more transparent, and less prone to bias.
Okay.
It's really dynamic field.
It sounds like there's a lot to look forward to in the world of generative AI.
Definitely.
Now, before we get too far ahead of ourselves,
Right.
let's take a moment to step back and reflect on the bigger picture of AI and its relationship with mathematics.
Yeah.
So we've covered a lot of ground in this deep dive.
We have.
From the basics of supervised learning to the mind-blowing world of generative AI,
Yeah,
it's clear that math is the driving force behind it all.
absolutely. It's amazing how different areas of math all come together in AI.
Like what?
Well, you've got calculus, linear algebra, probability statistics.
Yeah.
It's like AI is this melting pot for all these mathematical ideas.
It really is. It's like math is the language of AI, and we're just starting to understand how to speak it.
That's a good way to put it.
But with AI creating art, writing stories, composing music, it's easy to start imagining it becoming super intelligent,
Right.
like surpassing human capabilities. Do you think that's a real possibility?
It's definitely a captivating thought, and with all the advancements, it's easy to get caught up in the hype.
Yeah.
But it's important to remember that AI is a tool,
Okay.
a very powerful tool capable of amazing things, but still a tool guided by human intention.
So instead of worrying about AI taking over the world, we should focus on how to use it responsibly and ethically.
Exactly. AI can be a powerful partner helping us solve real-world problems.
Making the world a better place.
Exactly.
So as we wrap up this deep dive, what's the one key takeaway you'd like listeners to remember about math and AI?
I'd say the most important thing is that math isn't just some abstract theoretical field.
Okay.
It's a powerful tool for understanding and creating, and it's the foundation of AI.
That's a great point. And for anyone feeling intimidated by all the complex math we've discussed,
Yeah.
remember you don't need to be a math whiz to appreciate AI, just like you don't need to understand how a car engine works to enjoy driving.
Exactly.
You can still appreciate the amazing things AI can do, even without knowing all the math behind it.
Absolutely. And who knows, maybe this deep dive will inspire some listeners to learn more.
Yeah.
The more we understand AI, the better equipped we are to navigate its impact.
That's a great point. Understanding is key to harnessing the power of AI for good. Well, this has been a truly mind-expanding journey through the mathematical landscape of AI.
It really has.
I think we both have a newfound appreciation for the complexity and potential of this field.
I agree. It's been a pleasure diving deep with you.
And to our listeners, we'll leave you with this final thought to ponder. Is all this math just a way to mimic human intelligence? Or is there something more profound happening? Can AI truly understand the world like we do, or is it just really good at recognizing patterns? We'll leave those questions for you to think about. Until next time, keep exploring, keep learning, and keep diving deep.